Assalamu alaikum class. Today we are going to perform the lab of common base amplifiers uh, from your manuals. Uh, so we are looking at different biasing methods for our BJTs when they are being used as amplifiers. Last time around we used common emitter amplifier and we saw how it not only amplifies the input sine wave but also it inverts it. So here it is a case of common base amplifier. Uh, you will see that this kind of amplifier will amplify the output but it will not invert the output. That is, the input and output will not be 180-degree out of phase. There will be a small phase difference that you are going to find out, but that difference will not be huge as 180 degree. So the objectives of today's lab are to find the voltage gain AV. We all know what is voltage gain. It is V out over V in. So whatever output we will measure, we will have to divide it by the input voltage, and here I am talking about the sine wave or the AC input. And the second objective is to find the phase shift between input and output. Now I will explain a bit about common base amplifier that you must have studied in your theory. You must have also done DC analysis and AC analysis of common base amplifier. So as the name suggests, the base terminal is common in this type of configuration between the input and output. So we have a BJT which is connected like this, right? It is an NPN BJT. So this is N region, this is P region, and this is N region. So we will have to forward bias the emitter base connection. So this is emitter and this is collector and this will be base. So this will be negative biasing and this one will be positive biasing. And this one is an important connection, the base connection, which will be grounded. Now you can see this is the DC biasing of our transistor. In order to amplify any input, we have to give it an AC input. So here we will give it an AC input. So this will be a sinusoidal input that will be given at the input end. And of course, whenever we will give AC input, we must have a coupling capacitor in order to block the DC component. Similarly, for output, we have to take another capacitor and take the output here. So this is the V out. If I designate it, this is the V in and this is the V out. Now as you can see, the base terminal or the base connection is common between the input and output of the BJT. Hence this configuration is called common base configuration. And since it is using for amplification, today's lab will deal with how this type of configuration amplifies or given input voltage. Okay, so now before moving on, I must mention that you have to use the circuit that I will tell you here in this demonstration. Do not follow the circuit from your lab, because I think the biasing, the DC biasing values of resistors is not correct in the lab. I tried to implement it, but I could not find the desired results. That configuration does not yield a proper amplification. So don't follow the circuit from your uh, lab manual. Instead, use the circuit that I am going to show you here. I will also share these slides with you so you can easily follow the circuit. So this is the circuit that you are going to follow. Uh, you have to simulate it in your multisim, so you can easily find this type of this transistor. So in the manual you are using 2N3904 BJT, but here you will be using BC107 transistor. Other than that, the values of the biasing resistors and that of capacitors are also different. So you have to use all these values. The required components therefore are these: BC107 BJT, two capacitors, two resistors, function generator for generating sine wave as an input, and DC sources, of course, for biasing. So you need to have VCC, and here in this case you need to have VEE. The base is ground, so there is no DC source at base. So you have to implement this circuit in your multisim. Now, before going to multisim, I must tell you guys that you need to perform two types of analysis. Number one is DC analysis, and number two is AC analysis. So whenever you are performing the DC analysis, you have to forget about the AC inputs and AC outputs or coupling capacitors. You neglect them, or you open these capacitors, because you know that capacitors act as open for DC voltages, and whatever you are left with are the biasing resistors and the DC voltages. So the circuit that I drew earlier will be reduced to this one. This is our BJT. This one is our VCC. This is RC, and since this is ammeter, the base will be grounded. So this is VEE and this is RE. Now, by following the datasheet of this BJT and applying KVL, you can easily find the values of these resistors. The biasing voltages that I'm using here are 9 volt, and of course this is minus 9 volt. By applying these KVL equations, you can easily find what values of RE and RC are we going to use. But as you can see in the manual, you are already given these values, because finding this is a theoretical thing and that you need to perform in your theoretical class. You don't need to perform this thing here, but just for the sake of information I told you how to find these. So we have a circuit already that I showed you before. Okay, so here I should mention the two things that we need to find. The first is AV. This is voltage gain, V out divided by V in. So we need to find this. And the second thing that we need to find is phase difference. and this is given as theta is equal to frequency multiplied by delta t multiplied by 360. What is delta t? It is T1 minus T2, where T1 is time of V in, T2 is time of V out. So yeah, so these two things we need to perform. The circuit I have shared with you here. So what I will do, I will go in Multisim, and I have already imported the components that I need. So I need this transistor, I need these biasing values, these DC values, and these coupling capacitors. At input, I have used function generator. I have set the value of function generator to 25 millivolt. This is a peak voltage, so peak to peak voltage would be 50 millivolt peak to peak. So you have to use this value of voltage. You can also vary it to 50 millivolt or 100 millivolt, but don't go beyond that, because uh, but it is okay, you can go beyond that as well, as long as the values are less than these biasing voltage. You cannot use as an input 12 volt or let's say 20 volt, because the biasing values are very less. But so that's why we are using millivolts here. So in at the input we have used 25 millivolt peak voltage or 50 millivolt peak to peak voltage, and at the output to check V out we have used a oscilloscope. Now in order to measure the values, we will run the circuit and double click the oscilloscope. Here you can see the input and output. The input one is the red, it's the red in color, the waveform that is red in color, and the output is the one in blue color. By default, these both waveforms are in similar color. So what you have to do simply is go on the project screen and just right click on the wire and just select segment color, and from there you can select any color. Whatever color you will select, the oscilloscope will show that color of that waveform. So just it's that simple as that. And to get the white background you have to click the reverse. So if you will click the reverse, you will get black or white background. Now we have this input and output. That's what we needed. We needed an input, that is the red one, and we needed an output, that is the blue one. So it is amplifying the input. So we have input in the order of millivolts and the outputs in order of volts. Now you have to calculate what? You have to calculate the value of voltage gain. So here, how can you calculate the value of voltage gain? We have two. Okay, so now to measure the voltage gain, you need to know the maximum values of input and output. These are the two cursors that you will use to find the voltage gain. The first one, the red one, you can use it for the input thing. So you just need to right click it, select trace mark, select a trace, and you can easily select what channel you want to measure the value for. For example, we need channel A for the input. You can select this, and then you can right click and go to next Ymax. Okay, so it will move to a place where the input is maximum. You can also manually select it and move it here and there, but it will not be 100% accurate. So just you right click it and go to next Y maximum. So it will just jump to the next Y maximum. And as far as the output is concerned, you have to select a trace, select the channel B and OK, and again go to next Y maximum. Sorry, this one should be channel A. Okay, this one should be channel B. Right click both of them. Okay, so now you can see that the channel 1 or channel A, the maximum value for it is, as you already knew that it is 50 millivolt. So here it is showing that is 49.992 or almost 50 millivolt. So V in is maximum this. And what about this? This value is shown here. That at time is equal to 3.103. The value is 3.095. So the output maximizes to 3.095 volt. So this output has amplified. So now in order to calculate the voltage gain, you just have to divide the two values. So we have 3.095 volt divided by 50 millivolt. I will use the calculator for that. Divided by 50. Okay, and the 10 raised to power 3 will be multiplied, so it is 61. So the AV or the voltage gain for this particular transistor would be 61. So this is the first part. Now you have to measure the phase difference as well. We will go back to our multisim, and as you can see, you can tell yourself that the input and output both are not aligned. Although they are not inverted, but still they are not in phase. So what you have to do is change the time scale, zoom it in, right? Zoom it in and move it like this. Yes. So you can see the input is starting before the output. So you can move it here and move it here to a place where input is starting, and the second one, the cursor, you can move it here. Right. Okay, so here you can see this thing, T2 minus T1. This is showing you the delta T. As I mentioned the formula, this is the delta T here. So whatever the value in millisecond is given there, you have to put that value here, multiply it with frequency. Now what was the frequency? You just have to double click this, and I have selected here 1 kilohertz. You can select any other frequency, but I have used 1 kilohertz, so I will use 1 kilohertz here. So 1k multiplied by the time difference minus 194 So it's 1000 multiplied by 194 milliseconds multiplied by 360. Okay, so by multiplying this we get this answer, and because the difference is minus 194 microsecond or 190 microsecond, you can see that the point will move 6 digits here. So we have 69-degree phase shift, and since the output is starting later than the input, so this is minus 69, so minus sign will come also with it. So we have the phase difference as minus 69 degrees. So these were the two objectives of today's lab. You have to perform this lab on the multisim. You can also use the transistor that is used in the lab manual, but for that you will have to find out the resistor values, the biasing resistor values. Uh, so that's it from today's lab. Thank you.